Hello everyone, welcome back to the Thinking in Real Analysis series. In these videos, I hope to cover some basic analysis proofs and the canonical techniques used in them. Today, we'll be proving a statement about supremums, so let's dive right into it. The problem says, let S be a subset of the reals, be non-empty and bounded above. Suppose that for fixed C in the reals, C plus 1 over n is an upper bound for S, while C minus 1 over n is not an upper bound for S for all n in the naturals. Show that C equals the supremum of S. Alright, so to get a quick visual, here's our real number line, and we have some set S that is bounded above. The problem states that for a particular fixed value C, it has a property that every C plus 1 over n is an upper bound, and every C minus 1 over n is not an upper bound. Since S is said to be non-empty and bounded above, the completeness axiom tells us that it must have an upper bound. It is then reasonable to suspect that C is indeed our supremum of S. However, how do we prove that? Recall that by the definition of supremum, two things must hold in order for C to be a supremum of S. Firstly, C must be an upper bound of S. And secondly, any other upper bound for S, let's say B, must be greater than or equal to C, making C the least upper bound of S. So let's begin by showing that C is indeed an upper bound for S. We're going to argue this by contradiction. So suppose that C is not an upper bound for S. That means that there exists at least one element in S, let's call it X, that is strictly bigger than C. If no such element existed, then C would just be an upper bound. So what do we have now? Let's get a visual sense of what's going on. Here is C and here is X, and we're assuming that X is bigger than C. One possible way to approach this is to find a natural number n such that C plus 1 over n lies in between C and X. Since we're assuming C plus 1 over n is an upper bound for every natural, this would be our contradiction, because X would still be larger than C plus 1 over n, contradicting the fact that this is an upper bound. To find this n, we want 1 over n to be less than the difference between X and C. We can use the Archimedean property, which states that for every positive real, there exists a natural number such that 1 over n is smaller than that real number. So citing the Archimedean property, we specify 1 over n such that it is less than x minus c. Then, to get our contradiction, we simply add c to both sides of this inequality, and then the left-hand side becomes c plus 1 over n, which it should be an upper bound, while the right-hand side becomes x, which is an element of S. And this inequality successfully contradicts our assumption, since there exists an element of S which is bigger than C plus 1 over n, which means that C plus 1 over n cannot be an upper bound for S. With that, we can be sure that C is indeed an upper bound for our set S. Now, to show that C isn't just any upper bound, but it is the least upper bound, we again will argue by contradiction. Let's start by letting B be an arbitrary upper bound for S. We must show that C is less than or equal to B. Again, one way to approach this is by contradiction. So let's do that. Assume C is strictly bigger than B. Then C minus B is a positive quantity. Visually, here's what's going on here. B is an upper bound, which we're assuming is smaller than C. Just like last time, we can find a natural number such that C minus 1 over n lies in between B and C. Since we're assuming C minus 1 over n is not an upper bound, this would be a contradiction, since B is an upper bound and it's smaller than C minus 1 over n. To find this natural number, again, we can use the Archimedean property. Citing this property again, we specify 1 over n such that it is less than C minus B. Then we can negate this inequality to get that negative 1 over n is greater than B minus C. Lastly, if we add c to both sides, we get that c minus 1 over n is bigger than b. And since c minus 1 over n is assumed to not be an upper bound for s, b also cannot be an upper bound for s, contradicting our assumption. Hence, c must be less than or equal to b. And since b was arbitrary, c must be our least upper bound. Thus, c equals the supremum of s, and we are done. That is all for today. I will see you in the next video where we talk about cardinality of sets. Thank you.